Hi guys, welcome to chapter 12. We're going to talk about solids. We've learned in the past, throughout our educational career, that we have three phases of matter: solids, liquids, gases. Alright, here we're going to learn about the solids. What makes solids special is all the atoms in a solid bond together to make a certain kind of array. And then this array gets repeated. So, for example, ice makes a hexagonal shape array, and then that gets repeated. Right? This is called a crystal array. Right? Well, how can you find out what kind of pattern or array a certain solid has? X-ray diffraction from an X-ray diffracting microscope shows you. So here to our left, we've got an X-ray diffraction pattern for aluminum. Right? See how it repeats and it's pretty symmetric and all that? There's how you can tell. And each element is different. So that's an identifier for that element as well. Alright? So we have a crystal, a rock, some kind of solid. We take x-rays from it. We get our pattern. Alright? From there, a 3D model with computer mapping software can be done. And then we can make that fit an atomic model. Alright, and then that atomic model is something that chemists, biologists, we can work with. Alright, so here's an example of an array, how these are bonded together. Alright, this is actually not an element, this is actually vitamin C. Alright, so the different colors represent the different elements, but it gives you an idea of the bonding and structure that I'm talking about. Alright, so the bonding can be from ionic, covalent, metallic, or van der Waals bonds, right? Depending on the type of elements you have coming together to bond, the strength of the bonds, all that depends on what kind of actual bonding you'll get. So one thing that we can do with a solid, you can do this with any phase of matter, solid, liquid, or gas, so I'm introducing it here, because we'll carry it throughout this whole module. Right? Density is a property of matter. Right? So mass divided by volume gives you an object's density. Okay? So if you remember from grade school how to calculate volume, right? Length times width times height for a square or a rectangle, right? It's different for different shapes, so be careful with that. Okay? But if you take the mass of an object divided by its volume, that ratio is that object's density. Okay? Density is constant. It does not change. So it doesn't matter if I've got a cup of water or a swimming pool full of water. Density of water is still the same. Right? It doesn't matter how much you have. Because it's that ratio that's important. Alright? Well, we can do weight density instead of regular density, if you will. We'll just use weight instead of mass and get another ratio. Right? Same idea. The weight density stays constant just like regular density. The only thing different is now you're just throwing gravity into the mix. Because it may be a situation where you have weight but you don't have mass. You don't want to calculate mass. Well, you can roll with it that way too. Okay. Elasticity. How much stretch an object has, alright, specifically a solid, tells us a little bit something about it. So elasticity by definition is how much force an object can take and still return to its original shape. Alright? So here, we're one of those foam mattress tops, right? You lean on it, you get your handprint, but then after a couple of seconds, what? It goes back to its original shape, smooth top, right? So that's very elastic. Okay? Now, when you think elastic, you think, oh, rubber bands, bouncy rubber balls, things like that. But you don't necessarily think something rigid, you know, like metal being elastic. But when you think of the definition, right? Who can take a whole lot of force and bend but not break? Right? That's the whole object of being elastic. Right? So think about that and try out that extra credit right there and learn a little something. Alright? Elasticity Robert Hooke was a physicist who studied elasticity. Alright, now springs are very elastic. You can stretch a spring, and when you release it, it'll go back to its regular shape, right? Well, what Hooke learned was that the more force, the more pull you put on a spring, the more it'll stretch. And he discovered that they were directly proportional. Alright, so if I double the force, then I double the stretch. Okay? Tension and compression. You hear those words probably in everyday speak, but let's figure out what they mean specifically for us in physics. So if an object is pulled, that's tension, right? Tension on a string. We've talked about that a lot. If an object is being compressed, squished, that's a compression force. Okay? And you can have both happening at the same time, as evidenced in this picture here. Alright? You can also see it in this figure here as well. Alright? Now, tension and compression, we know with building materials, as we've just seen in the previous two pictures, that we've got to compensate for both tension and compression. Alright? But in construction, they use what's called an I-beam, right? Which looks like an eye if you look at it from the end on. Alright? But you got a lot of surface area on the top and bottom to handle that tension and compression. But you don't have the same amount of thickness. It's not solid in the middle. And this helps with the weight, right? Because you don't want to have a really bulky building because you've got all a solid beam instead of an I-beam, right? That just increases all the weight, and then you have to have more support, and you end up with a really ugly building. Okay? Now, just like having an I-beam is a way to help still support tension and compression that a building's weight will put on there, an arch, right? Whether it's the arch over here, like this in St. Louis, or an arch flipped upside down, being a dome, is another way to support a lot of weight with not a lot of bulk, right? Because an arch takes advantage of the capacity of the stone, in this case, to withstand compression, right? So you've got stones stacked going around in an arch, right, in a circular pattern, so they each support the other, and they can hold up a lot of weight that way. A lot of weight. Right. Chapter 12 also talks about scaling. Now, scaling is important, especially for architects and civil engineers, because they need a model to go by, not only to build, but to also see if they've got enough support for the weight, and if they've got enough strength in those supports to hold the whole area and volume of the building. Alright? So it's not only just a pretty little cute little house, it's actually got a vital importance, right? Because they can find weaknesses where they need more support structure, and so on. Alright? So, watch these videos, read your chapter, check out the extra credit, alright? Some of them are pretty good. And we will see you in class.